All right, grade 11s. Good Friday morning to you. Um, all right, so today we're going to be looking at transformers, not the robots in disguise, but other kinds of transformers, like ones that are specific for electricity. Okay, so yeah, Optimus Prime won't be making an appearance. Okay, or Megatron. But all right, so transformer. I just want to we'll do a little history, okay, of this device for you. Okay, so I just want to remind you, you have all the tools you need to understand this. So here, there's a little experiment here. If you can see the battery here, okay, now there's a switch. So there's a switch right here. If I close that switch, current will pass into this coil. Now, the coil is wrapped around a soft iron ring. Okay, soft iron contains domains. Okay, and these domains, the nice thing about soft iron is that they don't really stay magnetized. Okay, like so the domains will line up. If this coil becomes energized with electricity, it'll become an electromagnet, right? That'll cause the domains in this iron ring to line up, okay, temporarily while the switch is on. Okay, now this coil here is not attached to a power supply at all, and electricity will not pass through the iron ring. These coils of wire that you're seeing here, these are insulated wires. So they're coated with like enamel, which is basically like nail polish, sort of. Okay, and it's called magnet wire. And there will be no transfer of electricity to this coil through this iron ring. Okay, it's very important. But here's the deal. When you shove a magnet into a coil, we've already seen that that induces electricity, okay, in the coil. So here's the deal. In this first coil over here, the electricity will produce a magnetic field in this coil. That will magnetize the iron ring, and by magnetizing the iron ring, you're going to induce a current in the second coil over here. And here that coil is wrapped around a compass needle, and if electricity manages to get induced into the second coil over here, we should see the compass needle being affected by that. All right, so now watch carefully, okay, because the effect only lasts a moment. So when I close the switch, it's like shoving a magnet into the second coil over here, okay, but watch what happens. Okay, I'm going to do it now. All right. So if you saw that, I'm going to release it. I'll do it again. 3, 2, 1, press. Okay. So what happens is for a moment, when the switch is closed, but it's only for a moment, the needle dips, okay, and the red end of the needle points to the right. Okay. Now what's happening there is for a moment, electricity was induced in the second coil, and that caused like a brief dip, like this coil is wrapped around the compass, produced a magnetic field, and it dipped the compass needle. But if you notice right now, the switch is closed. Electricity is passing through the primary coil on this side attached to the battery, but no electricity is now being induced. It's off. The second coil is turned off, so it only got a brief pulse of current. But if you remember how induction works, you have to keep the magnet moving to produce electricity. So this experiment, when I close the switch, it's like shoving the magnet in the coil, but then it's just sitting there now. And so there's no further electric current being induced in the secondary coil. Okay. Now here's the weird part. If I turn the switch off, I'll get another brief pulse of electricity in the second coil because that's like pulling the magnet out. Okay. So watch, I'll turn it off and it dips. This time the compass needle dips, okay, pointing to the left. So the current was induced in the opposite direction. Okay, so watch, when I close the switch, dips to the right. When I open the switch, dips to the left. But in both cases, closed and open, there's no further action in the second coil. No current is induced unless I sort of keep going, right? So if I do this, I kind of get alternating current. Okay, if I keep opening and closing the switch, that's the only way for me to keep the electricity kind of going in that second coil. You can't just close the switch and expect it to keep going, because like I said, we have to change the magnetic field in the coil. keep it changing. Okay, if there's no change in the magnetic field, okay, then there's no current induced in the second coil. So turning it on will make a change just as you turn it on, okay? But then it's steady, so that's not going to work. That's why it turns off right away, that second coil. But then when you open the switch, there's a change that happens, so it induces a brief electric current in that second coil, but that doesn't last, okay? So here's the thing, with a battery, this device doesn't do very much. But now I'm going to show you what happens if we use a different source of current. What if instead of a battery here, we use something else? What if we used alternating current? Okay, that should keep things changing. So I want to show you that. And ultimately, this device becomes what we call the transformer. I hope you're still seeing this. Okay, so here, let's check this out. Okay, so what's happening here is the red wave that you see represents alternating current, okay, going in to this primary coil on this side. Okay, now in the secondary coil, again we have a soft iron ring. In the secondary coil, there's alternating current coming out. Okay, and what's happening with this device is current comes in on one side and then it gets induced on the other side with current coming out, okay, alternating current. And some students might say, well, what's the point? Why do we do this? Why don't we just connect the wires straight to whatever's on the other side? That device doesn't seem to make any difference. Well, the thing is there's a reason we call it a transformer, okay? What if I were to take the number of turns, the coils that are wrapped around this, and increase them on the secondary side? Let's see if I can do that. All right, so now if you take a look at this, I've got 3 windings of wire on my primary coil with electricity coming in, and my secondary coil, I've got a lot more. I've got 9 windings, okay, or 9 turns, okay, of wire, 9 coils if you like. Okay, and if you look, the voltage has changed. 120 volts are going in, alternating current, 360 volts coming out. So the voltage has been multiplied by 3. Okay, so what we've done is transform the voltage. Now I could also turn things around. Okay, let's say I do it like this. Now I've got more windings on the primary side where the electricity is coming in. So 120 volts. Okay, I've got 120 volts going in to the device with 9 windings on one side and only 3 windings on the secondary side and only 40 volts coming out. So you see what a transformer does. What a transformer does is it can raise or lower the voltage, and that is a crucial piece of equipment, okay, in our society. You don't realize it, but you use transformers all the time. Like your cell phone, when you plug it in to charge it, like my cell phone's plugged in, charging right now. That circuit can only handle 5 volts, okay? So my cell phone, digital electronics, are low voltage devices, okay? Your computers and your cell phones and your laptops and so on are low voltage devices. They run on anywhere from, let's say, 12 volts in a laptop, 12 to 18 volts maybe. Cell phone, 5 volts, right, for the charging circuit. But you plug in the wall is 120 volts. Okay, so the voltage at the plug that you're plugging your phone into the wall with is 120 volts. You need to transform that. You need to step it down to 5 volts before it goes into your phone. Otherwise, you're going to destroy your phone as soon as you plug it in. See, so transformers are used everywhere. Okay, like you see them all over the place. I'll show you some other images and maybe some applications you're not aware of. But every time you plug in toasters don't need transformers. Maybe your stove doesn't need a transformer because those are pretty crude devices. Actually, a stove will have for the digital circuits that you see, like the display and everything, they're low voltage too, so there will be a transformer inside a stove for that. But the elements probably don't use a transformer. But transformers do use everywhere. Okay, you're stepping up and down the voltage. Now, if you're really smart, you might have a question for me right now, and because we're doing this online, I'm posting a video, you don't get a chance to just interrupt me and ask questions. But are we violating the law of conservation of energy here? Because really, I've got energy seems to be being lost in this case. And if I do it like this, here energy seems to be gained for free. Like the transformer is not a source of energy, but yet the energy per charge has increased by a factor of 3 in this device. It seems like we're getting energy from nowhere, okay? But actually it's not true. The number of joules going in to the transformer and the number of joules coming out per second are the same. See, power, the number of joules per second, that's the number of watts, is voltage times current, okay? So when you raise the voltage, what's going to happen is you're going to lower the current by the same factor. So if I multiply the voltage times 3 in the transformer, I'm going to lower the current times 3. I'm going to divide the current, okay, by 3, I guess is a better way to say it. And so the product of voltage times current, which is the power, the joules per second, stays the same. So I'm not violating any law of conservation of energy here. A transformer that steps up the voltage will also simultaneously step down the current, okay? So we use transformers to control how much current we're transmitting through a wire, and that's actually a very essential application in our society, where how we power our cities and so on. All right, so we're gonna end this video for now, and then I'm gonna go to the notes and show you more. There's an equation that goes with this.